So now let's talk about how these atoms go together when they bond. And to understand that, we have to understand the electrons. So basically, when we fill up the atom, and I'm going to add a little bit to its nucleus here while I do this. There are 2 electrons in the innermost ring, and in the outermost ring, the most electrons we can have is 8. Atoms always want to have a full ring. So if it's that innermost ring 2, every other ring is 8. And so we usually think of this as them wanting to have a full 8. And this is something called the octet rule, because octet means 8. So to get their 8, what this means is that the atoms have to get electrons from other atoms. Now, if you have 7, like this guy here, you are much less likely to give up 7 of your electrons to get to that full orbital. Instead, what you're going to want to do is you're going to want to accept an electron from someone else. And if you have 1 electron in your outermost orbital, then you're going to want to get rid of that one. So atoms now have a choice. What they can do is they can give or receive electrons. This is called ionic bonding. So let's take a minute and look at what that ionic bonding looks like. Okay, so if you are an anion, if you have accepted that electron from someone else, now you're negative. And if you're a cation, you have lost an electron. It's important to note that opposite charges are going to repel. So you can see with this electron that I'm moving around the screen, I'm actually able to repel the other electron. On the opposite end of that, if you've got opposite charges, now a positive and a negative, they attract each other. So one of the ionic bonds we talk about the most is salt, sodium chloride. And in this, sodium gives an electron to chloride. This makes sodium positive and chloride negative. Now they're attracted to one another because they have those opposite charges. And even though these ions are bonded to each other, in this case ionically, it's important to note that there's still kind of a positive end and a negative end. And these are going to line up. And that's because in the end everything kind of wants to be neutral. What this means is that when you look at the salt on your table, those salt crystals are tiny little squares, and that's not because anyone cut them up like that. It's because when those sodium and chlorides come together, they come together in a very specific formation because basically everyone wants to be happy and they want all those positives to be near the negatives. And the atoms, if they're in a vacuum, are bound tightly together. In biology, we always think of things as being in water. And once they're in water, these ions are able to separate and go their separate ways. The other option here is for the atoms to join sort of like a shared custody agreement. And this happens with molecules like oxygen, where basically you end up with some of the electrons being shared between the 2 atoms. So nobody's given up their stuff, but they're sharing. The problem is that this means that you're kind of tied together. This is called a covalent bond. Now, if you walk into my biology class, I'm going to tell you that covalent bonds are the strongest bonds. If you walk into a chemistry class, they're going to tell you ionic bonds are the strongest bonds. Who's right? It turns out that it's situationally dependent. If we think about the bonds as occurring within a vacuum, ionic bonds are the strongest. But in biology, we always think of everything as being underwater, and water, it turns out, is the kryptonite for ionic bonds. It breaks them. And since the water breaks those bonds, we think of them in biology as being relatively weak, and those covalent bonds as being very strong. But why does water have this special power? And that comes down to the fact that water is held together by a covalent bond. But water is made up of two atoms. You have hydrogens, or two types of atoms, I should say. You have hydrogens, and a hydrogen is a teeny, teeny little atom. It's got a proton and a neutron and one electron. And then it's got oxygen, and oxygen has 8 protons. Now, what does this mean? As I'm putting all these things together, it should become apparent to you that oxygen has a much, much larger nucleus than the hydrogen. And what this means is that the oxygen nucleus, because it's got all that good positive stuff in it, in this shared custody agreement, it's going to be a bit piggy. It is going to hold on to the electrons from the hydrogen more often than the hydrogen holds on to them. And this leads to something very special. This is called a dipole moment. Basically, the oxygen has a slight negative charge because it's got extra electrons a little more often, and the hydrogen has its electrons less often than it should, so it's got a little bit of a positive charge. This creates something where basically water looks kind of like Mickey Mouse. And what's going to happen in water is that opposites attract. So the positive charges, the negative charges are going to line up. Now, this creates something kind of cool. What it means is that when we put something like an ion in water, since it is charged, it can mesh with these positive and negative charges on the waters, and it can kind of go with the flow. But if we put something uncharged in, like oil, think about putting oil in water, what happens? It clumps. And that's because these charged things are really unhappy if they're near uncharged things. Everybody wants to be neutral, and they can't get there if they're next to something that is neutral. And so they exclude it. This creates something that we call hydrophobicity, which means water fearing. Something that goes with water is called hydrophilic, and this means it's water loving.